This is to prove the sweatshop theory. My computer refuses to show So before getting into the scientific part, I thought I'd make one or two remarks about our liaison when I met Dick. I met Dick in this place. This is the Berkeley campus. It was quite a long time ago, and so in my memory, the sky was always like this in Berkeley. Actually, I started off my astronomical career here in Toronto, and that was so long ago that in my memory the sky is always like that in Toronto as well. So this was a publicity shot of Berkeley. So we actually met in the building on the left here, which is Campbell Hall. This picture, which you saw over George, was taken in the room right here. And my office was this one. And I've forgotten now, Dick, where you were, but you were up in one of these offices up here.
I was in the office that had a split in the wall to give me confidence in the engineering.
Now that's the next part of this. So I remember, so this is again was a UC publicity shot, and it actually looked pretty much like this on the outside. But actually, when I was there and Dick was there, it was about 1980. It was still a bit in need of paint on the inside, and actually, if you look at this carefully, you find the paint was not that good. And my office also had a faint crack in the wall. So I was interested when I went back to Berkeley last year. I discovered that they actually hadn't changed the paint job since then, and the crack was now this wide. And it's impressive, and they are supposed to knock this down and give them all a nice new building when the California budget improves. So let's see who that is. So I look back over the years and turned out, French, doesn't show on the screen or something. Well, never mind. Dick and I have only 4 papers together according to ADS. This was the first one, with Alex Larey. I think this was the contamination by the Russian school we heard about before. We all thought we should work on neutrinos and why neutrinos were dark matter. We didn't really understand how it was going to work. And if you look carefully, I did highlight this, but you can't see the highlighting. Just the schematic calculation. We only did a 1D simulation. The 1D codes are easy to write. So the schematic calculation of how neutrinos would clump around a galaxy suggests that properties of neutrino clusters depend only on seed mass substantial and seed separation. Their mass and velocity dispersion may be quite comparable with values inferred with halos of galaxies. we were claiming here that we can make galaxy halos out of neutrinos. Now, this was actually 1983, both of us in the same year. Wrote other papers saying it was completely impossible. You know, maybe this is why we only have 4 papers together. The next one was, this is again 10 years later. This is with George, 1992. Kobe, anisotropy has just come out. We look at large-scale structure screening motions. Surely you know now we can see the light. Well, if you look at this last conclusion, this shows you how in the past you remember things selectively. Spatially flat CDM universes with omega of about 0.2 and a cosmological constant require the mass to be substantially more clustered than the galaxies in order to be consistent with Kobe, with observational screening motions. They're then in conflict with our versions on small scales. We were actually ruling out lambda CDM in this abstract. Even though George showed us a plot showing how he proved lambda CDM a year earlier. So I think this shows you that retrospective memory is not always good. Also maybe why. I also may show why in later papers, the next one where we were actually on the same paper had 25 authors, and the most recent one had 250. So we need additional help if we're going to get the right answer. So I'm going to talk about modeling the galaxy population, by which I mean not just one or 2 galaxies, but the whole galaxy population in this universe. So here are 3 observational things, all of which Dick's interested in. So you've heard a lot about this one. This is a 2DF survey, half-bit. Dick, we've heard about his ideas about linking the galaxy distribution on large scales, so we know lambda CDM is some bias that predicts this. We heard less about this, but there's another one which Dick is very interested in, which is using the Lyman-alpha forest from the gas structure. So this is the Lyman-alpha forest of the quasar. This is the simulation. They look very very similar, and you can actually use the statistics, and it seems to work. And that seems to say that the intergalactic medium of redshift 2 has small-scale structure, smaller actually than the scales of 8 galaxies, which is actually just at the level you'd expect. So it seems the initial conditions match the model, the large-scale structure today uses the model, and the small-scale structure just before the galaxies formed also matches the model. So it should be easy. But as Jim pointed out, it's not that easy. So I'm going to talk about things based on millennium simulation and offshoots to try and study the galaxy formation. So this, of course, is the dark matter. We finished the simulation in 2005. And then we used it to build simulations of the formation of the galaxy population. So I want to stress the word simulations. What we did is take the history of the dark matter distribution, extract it, write down simplified differential equations for what we think the baryons should be doing, and then integrate them down to things. So this is a poor man's simulation of the astrophysics. It's not just some recipe where you put galaxies in halos without saying anything about history. And that allowed us to make plots like this. So here's the 2DF, or here's the CFA survey, and these are actual galaxy catalogs where we, in a rough way, calculate the formation of every galaxy, finding its history, its magnitudes, and so on. And then you can do some statistical comparisons and figure out it's not doing such a bad job. And because it has a simulation from the beginning, you've got light tones. So this is us. You can't read this, but this is redshift 1 is here somewhere. 2, 3 is a thin light show. This was a mock catalog to compare with the Cosmos data. And this is very useful for the observers because they want theoretical models to compare with. And so I think one of the reasons this became so popular was just that we made things that the observers could compare with, and we made them publicly available. So this has led to considerable success in the fact that we tried to keep accounts. So we found that a couple of days ago, we already had 307 papers on the archive actually directly using numerical data from the simulation. And most of these were by people who've just taken the data from public archives. A lot of them, of course, are using it rather peripherally. And most of them were actually based on these galaxy catalogs because, for example, the people doing the Cosmos surveys were using the galaxy catalogs to test their algorithm, because at least in the simulation, you can go back and see what it was in 3 dimensions and see if you got the right thing. So it's very useful. So as George says, if you want to get citations, you want to get people, you have to make your work available in a way that other people can actually use it. Nevertheless, there are serious limitations. So some of the limitations are for lots of projects. With a big simulation, but it's too small. If you want to get the statistics of the baryon acoustic oscillations, the simulation was only half gigaparsec on a side. It's not big enough. You need to be 3 or 4 gigaparsecs on a side. On the other hand, although it was in its way a high-resolution simulation, the resolution is finite. You can't see very small objects just because the mass resolution is not good enough. In particular, you can't model the formation of small galaxies just because you can't see things that mass in simulation. The more numerical problem is you take this, for the dark matter there are lots of tests. People know when you can believe the results and where the limitations are. For all these galaxy models that people are doing, you just have to take it on trust. Are you sure there's a numerically convergent result? You have to find a way to do it. Another problem, we choose the WMAP1 cosmology. Probably not the right one. It'd be nice to know how the results depended on the cosmology. And so, what limits the use that people can make of this is the fact, you have to take what you're given on trust. You can't go and try a different cosmology, you can't go and change the way the thing's doing, you can't actually play with it yourself, figure out what you can believe and what you can't. So we're trying to change all of this, and what I want to show you is where we've got so far. So, Alex yesterday said there's only 1 millennium. I'm not quite sure what you meant by that. It's a very strange view of time. Let's not even prove simulations because we have millennium 2. There was a simulation which we finished in 2008. So it's exactly the same long cosmology, same number of particles, but it's a fifth of the linear size, which means that the mass resolution is 125 times better. And still has a very large number of objects, so there's just a series of zooms down to a single object. And it's processed in exactly the same way as the larger volume. So this makes it possible to do direct resolution tests over a factor of more than 100 in mass resolution. And also, when you get some confidence, then you can start studying the formation of much smaller objects. I'll talk about it. So here's the first test. This is, the only thing we want to do is compare with new data, because the data got a lot better. We first look at this is the mass function from the slope to a final release to the slope to the sky survey. This is the stellar, the abundance of gas function of stellar mass. This is 5 orders of magnitude. Look at the size of the error bars. So this was what the Gaussian University got the model on the Millennium 1, this red curve. You run just exactly the same galaxy formation model on the 100 times higher resolution Millennium 2, you get this. You see they converge very nicely down about here, at less than 10 to the 10 solar masses, and then the resolution just fails in the original simulation. So that's the resolution model. The other thing you see is the model doesn't fit the new data. Fit the data that were available when we wrote the paper, more or less. The data got better. So I'm going to spend the rest of the time telling you about the next generation of these models, which are implemented on both the simulations simultaneously. And this is done by Rex Manchi-Wall, who's now a postdoc in Durham, and this paper will be on after a PhD this week. So the idea is to implement modeling of both simulations simultaneously, so you can test things, you can test the convergence of all the galaxy properties near the resolution of the Millennium simulation. Once we understand that, we can then extend down to much smaller galaxies, because we have 100 times better mass resolution than we did before. Then we took the opportunity, since the original simulation, people pointed out lots of things that were wrong, or were treated in a very rough or inappropriate way. So we did our best to fix up the treatments of the things that appeared most troublesome, things with sizes and star formations and so on. And then, of course, these models, we have efficiency parameters describing things that we don't understand very well, so we readjusted those to fit the new and more precise data. And then the idea is once you get the models fit, you can test them using these simulations against all the new clustering and redshift evolution data. So let me show, I'll start by showing you things that work well, just to convince you that we can actually get really quite good fits to a very large range of data. And I'll finish by showing you things that don't work well, which will come back to Jim's talk. So here's the mass function again. It's slow data again. And this is 5 orders of magnitude in stellar masses. Very wide range in how we get good data. And now by readjusting the efficiency parameters of the various processes of star formation and feedback mostly, you can get a very good fit. And again, you see this is again the convergence test. If you times 10 to the 9 solar masses, they agree, and then there's not enough resolution in the bigger volume simulation.
So how many parameters do you have to set into this?
I think it's not a matter of fitting parameters actually, because you have to. What you find is when you have data of such a wide dynamic range, it's not just changing parameters. You find the original parameterizations you have just won't fit. You actually have to change the modeling altogether because you're basically fitting functions. So with this much dynamic range in this matter, it's more than just fitting parameters. And I'll show you there's a very wide range of data, so it's very difficult to count actually. But what you can think of is with better data, you're kind of, with your underlying hypothesis, you're measuring the efficiency of various processes of function, for example, the mass of the galaxy.
You just need to see the data.
Which one is it? Well, this mass function here. These are two different data sets. So the Swan survey needs to have completeness corrections when you get to these very small dwarfs because there are surface brightness limitations, which weren't taken into account in the larger analysis here. So that's the reason why there's a change in color of symbols. You can convert that to luminosity functions. So these are slow luminosity functions, G, R, I, Z. Now this is 9 magnitudes. Okay? The limit here is minus 15. And curiously enough, while you here see in stellar mass, the model slightly over predicting. Luminosity functions are slightly under predicting. So I haven't quite figured out whether this is in the data or in the models that there's an issue here. You can go to much smaller objects. So now you go to your high resolution simulation, Millennium 2, find all the objects which are isolated, disk galaxies, the disk is much more massive than their bulge, and have a stellar mass equal to the stellar mass of the Milky Way, and then just count satellites around them, about 1,500 of them. And then if you've got the abundance of those satellite galaxies, it's a function of magnitude, going all the way down to -5 now, it's another 10 magnitudes. It's 10 magnitudes. There's a total range of 19 magnitudes. And the prediction for it, then it depends on what you do about reionization. So we don't really know what the right answer is. Our preferred one is this one. So this is the median prediction, and it's up for another 10% points. These are the classical dwarfs around the Milky Way, and these are the faint dwarfs, the weakest correction recently. You have this, which is an older version of reionization, which has somewhat stronger effects. You can see that the predictions move down. But basically, it's very close. Of course, related to what Carlos was saying. If you have no reionization at all, it still fits for most of the range, but maybe it fails a bit at the faintest ones. So this model is fitting now with this full range, more or less. These are the colors of galaxies. So this is from 10 to the 9 solar masses to 10 to the 11 solar masses. So that's the range of most of the star-massive stars. Sloan data for volume samples of the red histograms. The model, the black one, color distributions are fitted reasonably well. These relations, this is the size of the stellar disks, this is the median, similar. These are from Sloan data for disk galaxies. Okay? This is the metallicity. It gets mass all the way from 10 to the 8 to 12, gas mass. This is Sloan data for these are the small dwarf galaxies. Simulation. Here's the Tully-Fisher relation. Luminosity from -15, -23. 8 magnitudes. This is the one sitting scattered in bins. This is a sample from the SIBO of 4,000 galaxies just binned up. These are the bulge sizes. This works less well, as you can see. That's more or less on the right side. So you can make predictions of these things.
What's Vmax?
This is the max. Yeah, that's important. Technical issue. The velocity that's put in here is the maximum velocity of the dark matter halos. So of course, there isn't any dynamics in here. Now here's an interesting one. This is the correlation. I don't know why it's cut off at the top. Live with it. This is the galaxies from about the mass of the Milky Way, up to 10 times more massive, in 2 bins. This is their autocorrelation function measured from the slope, from 30 milliparsecs down to 20 kiloparsecs. Look at the error bars that's slowly living up here. The model is like that. This is the model of a more massive galaxy, measured directly from the simulation. The blue and the black are the 2 simulations. So now you can see the convergence between the 2 simulations, but I'll come back to that. This one I find even more remarkable. So this is projected number density of galaxies in clusters. So you look at a projected cluster and you count galaxies as a function of distance to the center. This is the projected number density as a function of the center, stacked. For clusters with galaxies more than 10 solar masses and clusters in this mass range. It's actually a galaxy count range you have to use. And this is done in such a way you do exactly the same thing on the real Sloan data and on the simulations. So first of all, look at the red and the black solid curves here. That's the 2 simulations differing by a factor of 100 in mass resolution. You can see they're lying on top of each other exactly. So even for this, there's almost perfect convergence between the simulations. Now look what happens if you only in the simulations take the galaxies that actually still have an identifiable dark matter substructure. In the Millennium simulation, that's this red dashed curve. In the Millennium 2 simulation, it's this black dashed curve. So what happens is when you increase the resolution of the simulation, you can see small little lumps of dark matter inside the big ones. So it goes up. But even at the higher resolution, you don't get the right answer. You have to take into account of galaxies who in the simulation actually lost the dark matter halos, otherwise you don't fit. And that's what's been done here. So the fact that we get convergence shows that the way we do this gives you very good convergence, usually changing the mass resolution by a factor of 100. And this is then the result of the slope. You can see it's very close, just slightly less concentrated, which may be significant, as I'll come to in a second.
And what fraction of galaxies don't have any halos?
In this case, inside here, it's about 60%, and for the red curve, and about 20%, 17%, I think, for the black curve. So this is coming back to Jim's point. So now in the simulation, you can go and ask for each dark matter halo, and we've simulated, we think we know what the stellar mass of the galaxy inside it is. This is the mass of the galaxy as a function of the mass of the halo. Except the mass that's plotted is not the present mass the halo has, the maximum it ever had over its past history, which maybe is closely related to what you think would fall inside it. So the symbols with arrow bars always actually down in the simulation. And the blue curve is what you get by a very simple counting argument where you just make a one-to-one correspondence between the abundance of the halos in the simulation and the abundance of the galaxies in the universe. So what you see is they work quite well. The scatter predicted by the simulations is significant but not very large. So it seems that we know for a typical galaxy with a given mass, here somewhere, we can predict what its halo mass should be. And the interesting thing is you take the mass of the Milky Way, down here, here you can read off the mass of its halo, which is a couple of times 10 to 12. If you know the mass of the halo, you know the mass of the galaxy, you know the efficiency with which the baryons inside this galaxy turn into stars. Okay? Turns out to be low. Maximized around 20%. So this is just saying that most of the baryons in today's universe are not in stars, they're somewhere else. And that's even true halo by halo. The maximum you get is 20%. If you look at the simulations people publish of individual galaxies forming, they're all higher than this, with a few exceptions. And the distressing thing is, the better the simulation looks, the worse it agrees in this parameter. So, for example, this is a very recent, can't see it very well here, simulation by a group in Zurich. It's a very nice plot. If you were working there, you will see. It's a very nice thin disk galaxy with a small bulge and beautiful spiral structure. Looks a perfect lake-type galaxy. If you look at the mass of stars in their galaxy and the mass of their halo, it's up here. So by a factor of 3.5. Some of Fabio Govinato's nicest ones, one of his favorite ones is here. These two closer, but still about a factor of 2 high. The ones that are down here, there's some of mine, or actually see this down because they look better in this plot. They look a whole lot worse if you make a picture. Because actually they have most of its bulge. So we have a situation, you can make a nice disk, but then you've got the efficiency wrong. If you get the efficiency close to right, you don't make a nice disk, so we still stop. Now coming back to things that work less well on galaxy formation modeling, which is always the most interesting thing, of course. Let me show you some more correlation functions. I showed you these two before, where it works very nicely. Let's go down another order of magnitude in stellar mass. Okay. So this is now down to below 10 to the 10 solar masses. But first of all, look at this. This is slightly impressive. Look at this panel or this panel. The dashed blue curve is the Millennium 2 simulation. The black curve is the Millennium 1. So there's a factor of 100 in mass resolution. The clustering agrees perfectly with the other simulation. Fails to agree with the data. And it's interesting that it agrees quite well on large scales. It fails on small scales. And I think this is just a reflection of the fact the over amplitude of the clustering assumed in the laser is too high. You see the sigma rate value to be 0.9, should be lower. And the result of that is there are more massive halos, those have more galaxies, and when this part of the correlation function comes from galaxies inside the same halo is too high. That's why this is too high. We need to reduce simulation amplitude. Here's something else which doesn't work. This is the stellar formation history of the universe. And the data. This is what's predicted by the simulation. It peaks here, redshift 3, then drops. So it fails to match the data in two ways. One, it's low everywhere. And secondly, starts dropping too early. And the fact that it's low everywhere is a problem with the data, because the star formation rates the observers quote from the universe are not consistent with the mass density of the stars which they quote from the universe, so you can't get both right. And we normalize everything to fit the mass density, so we don't get the star formation rate right. But the shift in the peak is also significant. That you can see from the... Oh, here's something else that didn't work. The color distributions. Now I go even fainter objects. This is 10 to the 8 to 10 to the 9 solar masses and stars. You can see the simulation, which is a full curve, plotting lots of red galaxies, whereas in the slow data, all the galaxies are blue. So there are too many red and dead small galaxies in the simulation. The overall number of galaxies is right, but too many of them have already finished their star formation. This is my final plot for this kind. This is now the abundance of galaxies as a function of their stellar mass by redshift. So this is low redshift. Let's go that to 0.5. Is out to redshift 1, redshift 2, redshift 3 to 4. So of course, it still fits a low redshift, that's how we set it up. But you can notice by the time you get to redshift 1, we're high. For all the galaxies below about a few times 10 to the 10 solar masses. So, of the massive band, we have quite a number of massive galaxies, you can compare it to the green line in this plot. But we're over-predicting the number of low-mass galaxies. So the problem is, in the real universe, the low-mass galaxies were formed later than in the simulation. So again, the conclusion is the same. Star formation is too early. We have to push it to lower redshifts in this model is suggesting. So what I hope I convinced you is, with this kind of simulation data, with a particular model, you really can make precision tests against the real populations. You should check the abundances, so the mass functions and luminosity functions, the scaling relations, and the clustering. There's not enough to get all that right, you have to get the history right as well if you really want to believe it. So the conclusions from a scientific point of view this seems to give you is this amplitude is too high, everybody else would agree with anyway, and the current star formation models are producing too many stars at high redshift, particularly in the low mass objects, and this is true for the model I've shown you here, but actually most other people's models also give similar conclusions. So I think we need a better understanding of star formation. Shannon might disagree with that, I'm sure. And we need a lower fluctuation amplitude in the simulation. So I will stop there, except for wishing you a happy birthday again.
Questions or comments?
I'm not sure that your problem with star formation history can be explained by what you said was discrepancy of observation between star mass and star formation rate. And really, I think that if you look at this mass assembly and star formation rates, they are discrepant just at higher redshift. They agree very well at low redshift where you were having a problem.
Well, I think I agree with that. I mean, the problem is it's very difficult to make progress until we sort out whether we believe our star formation rate indicators, because there's this overall discrepancy between the integrated cosmic star formation and the number of stars. So we have to sort that out, whether that's because of variations in the initial mass function or some of the indicators need recalibration. If it's the indicators, then you know, the recalibration probably is a function of redshift, and so that may change the shape of the curve. So until the observation situation gets clarified, it's hard to make progress. But I have good hopes that in fact Kershaw will make big inroads on this. So I think within a year or so, it could easily be a whole analysis.
So all your comparisons are based with observations of stellar masses.
No, I showed you the luminosity
Well,
functions,
most of the
color
data-
distributions. I didn't show you the morphology problems.
Many of your conclusions, many of the way you split samples compared to clustering and so on. The stellar masses are finding the models that predicted that there's not enough observable to go from what you actually observe. The stellar masses, you make a number of very certain assumptions. You just mentioned one of them, the IMF. So why do you think this is the right methodology?
I feel very strongly that's the right methodology, for the following reason. The conversion from the observed properties from the observed properties of stellar mass depends on the IMF, on stellar evolution, stellar atmospheres,
Dust.
on metallicity, and dust. So So I think the stellar population from the list is reasonably well under control. I think the dust is not under control at all. So the colors depend very critically on the conversion between colors and obscuration, so it would be E minus, B minus V, and AB for people who know. This depends critically on how the dust is distributed relative to the stars. And we have no idea how to do that, even at redshift 0, let alone high redshift. So I think the correct thing to do is actually, but what the observers do know how to do, is to construct of these things like the stellar mass, which are relatively insensitive to dust properties by combining colors. We demonstrated this. So rather than putting in some model, like you put in an arbitrary distribution of the dust relative to the stars and then try to calculate their properties, I think it's much safer to calculate things as a function of stellar masses and star formation rates and let the observers make the corrections as well as they can. And the IMF is not an issue here because the observers also make an IMF assumption. So as long as the IMF assumption made by the observers is the same as made in the modeling, then you can compare the two consistently.
You just told me they're getting it wrong, because star formation rate doesn't add up to the stuff we see today. Clearly it's doing something wrong.
No, that's not correct. I mean, if there's something wrong, we're not going to make it better by trying to predict O2 fluxes. Because clearly the misunderstanding is how you go from the O2 flux to star formation rate. We're not going to do that by doing this kind of theory. We have to do that by finding different observational indicators and making them consistent with each other. That's exactly what Herschel is doing.
So if we take the assumption that these conversions are reasonable, what about the IMF conversion? Does that appeal to you as a solution model or not?
Well, I think what Herschel will tell us is whether the different indicators of massive star formation are consistent with each other. The conversion to the total mass depends on the low end of the IMF, and there's almost no direct observational constraint on that. So you have to go for indirect constraints through dynamical measurements and masses, which are much less certain. So we have to keep doing that, but I think it will be difficult. There have been decades of work on this. It's very difficult to get convincing conclusions. I mean, there are some indications that the IMF is changing, but they're very controversial.
I think we've got to move on.